Hello all of you. So in the last lecture we have been discussing the theoretical basis of the molecular simulations and how the molecular simulations can address the challenges that we saw in the lattice model. So today I will take it further and discuss about the molecular dynamics approach in a little bit more detail, and I will focus more on how do we capture the interactions. And after that, in this and the following lectures, we will be discussing how can we think of another method, that's the Monte Carlo method of the simulations that essentially captures the same kind of thermodynamic behavior. So just to quickly recap what I have been telling in the last lecture is we can think of the phase space as the space formed by the momenta of the particles, and I used a collective or compact representation P for all the momenta of all the particles and all the coordinates of all the particles. These are 3n variables. These are 3n variables. The only reason I am doing a 2D plot is because I do not know how to do a 6n dimensional plot. That's simply impossible. And then I said that I can represent a phase point as some gamma that represents the state of the system at a given time in terms of our ensemble based idea, that is kind of a micro state, or we can refer as state. And then I said in reality this is all the information that we need. If I know what is the phase space, since Hamiltonian depends on the phase space, the P and Q, we have the energy and we can do the all thermodynamics that we are interested in. Simply it is impossible to do that because you may imagine there are infinitely many trajectories starting from infinitely many state points which are possible out there. But what is possible, and that is what I was starting to claim, is the starting from a given state point or few state points. I mean, I can do simulations from various configurations and look at the trajectory of that particular state. And this is, when I am looking at this gamma t, is the basis of the molecular dynamics or MD simulation. So although I have drawn the trajectory here, we should not confuse this with the actual motion. So I am not saying that the molecules are moving in this way or the system is moving in this way. This is a trajectory in a phase space that is formed by the momentum and the coordinates, right? So it is not very intuitive to look at the shape of the trajectory and make any clear inference starting from there, right? So keep in mind that the trajectory is there. Using that, I can infer information, and there is whole mathematical apparatus for doing that. But as it is, the shape of the trajectory is not too much to worry about right now because it is not very intuitive on the shape that we can say anything is happening. So then let us see what we will then do in the molecular dynamics. How will we make it happen? How will we get gamma of t? So what I will do is I will start with a system, or what is typically done, I will start with a system of certain number of molecules and I will place them in some kind of a box. So these are the molecules or particles in the system, and there are n of them, and all of them are essentially moving, and it is their generalized coordinates that can be in any coordinate system or Q, and their generalized momenta, that is P, that is essentially a collection of Q1, Q2 and so on, and P1, P2 and so on, if we have labeled the particles in any particular way, right. So, they are evolving, and therefore, if I look at the evolution of the system, we are essentially evolving using the definition of Hamiltonian, that is a function of P and Q, and at any given time you will have a particular value of P and Q, right. After very long time, and there is a name for this, it is called Poincare recurrence time, the molecules may come back to the same configuration, but you may imagine that for a large number of particles that is not really going to happen. So, if you are interested, it is called Poincare recurrence time. That is when you can revisit a state, or in terms of our trajectory kind of a logic, it may be something like that. So, whenever we cross the same point, so we are revisiting the same point in the trajectory, and when that is happening, I mean, like intuitively you can see from diagram it is happening, but in reality, since we are running only for a finite time, that will seldom happen for very large number of particles. So, after so much time it may come back, but essentially for all we care, we will have unique states of the system corresponding to different value of P and Q for most of the time. So, let us say we have a mechanism to evolve this, and I will come to how to do that, and let us say we are able to find how this gamma t is changing with time, right. Now, you may imagine that if I am having some kind of an analytical expression, then clearly I can solve in this continuous domain along the trajectory, but any kind of a numerical method will not be quite doing that. So, essentially what you will be doing is solving for small time points and using those time point values we can then infer the trajectory. That is nothing to do with molecular dynamics in general. Whenever we are doing things numerically, we always have to discretize the domain or the where the motion is taking place. I am moving in the phase space here, so the motion is not like a linear motion, but nonetheless you will be typically solving for a finite value of finite intervals of time. Let me call that some delta t. So, then I can, since at every phase point using the Hamiltonian I can find the properties, and let us say I am interested in some property m of t, this can be anything. So, let us say at every time point I can evaluate that. Then if I take the average value of that, this will give me the average value of the property of interest that I am working in, right. So, essentially in our logic, this is going to be something like 1 by tau sum over j is equal to 1 to some tau divided by delta t, and I am describing in a minute, m of j or m of j multiplied with delta t. What I am doing essentially here is, let us say if I am running for, so tau is my total run time of the simulation. So, then I will be making tau by delta t md steps that will correspond to different lines that I am drawing here, and for each of them I will be computing the property value, and the time value is j multiplied with delta t, and if I sum over all the property values and divide by the total time, I will get the basically arithmetic mean of that, and this is what I will represent as the average of the particular property that I am interested in, right. So, this is, I would say, the basis of the molecular dynamics. Now, try to see how exactly I will find the Hamiltonian, right. So, essentially the scheme goes like this. So, I assume that the particles are classical, and by classical means several things here. First of all, whenever I say the particles are classical, that means they are moving like, say, a typical example of balls or the pieces on a carom board, right. So, when that is happening, so one of the things that is an outcome of classical mechanics is that the energy happens to be no longer quantized, right. So, in quantum mechanics the energy is quantized. In classical mechanics there is no such thing, the energy is like really continuous, right. In fact, quantum mechanics is what is valid for a very small scale. If I really go to within a molecule or smaller scales, then it is indeed true that the energy is quantized. But if the total energy is very large in comparison to the quantum units, then in that case that assumption is barely important. Let us say if quantum unit or one quanta correspond to something like 1 in some unit of energy, and let us say we are dealing with billions of that energy units, then in that case the fact that energy is changing in the units of 1 is barely important, because the energy unit is so small in comparison to the energy of the system, right. So, that quantum mechanical effects vanish in the regime of classical mechanics as long as we are dealing with much larger systems than compared to individual molecules. What this also means is, if the particles are classical, then they have to follow the Newton's laws of motion. And what do I mean by the Newton's laws of motion? It is simply F equal to ma. So, first of all, I can say energy is continuous, and I will revisit this point in a minute. And the second thing I am saying is the particles follow the Newton's laws of motion. So, when the particles follow the Newton's law of motion, that is F equal to ma, and that is true for every particle. So, let us say if I look at particle I, we will compute the force acting on the particle I, and this has to be equal to the mass of the particle multiplied with its acceleration, and both acceleration and force are vectors. In terms of our generalized coordinates or any coordinate, I can write this ai as the second derivative of my qi, right. So, we can find the positions. The first derivative is my velocity and the second derivative is my acceleration, right. So, then if I know the forces, I can know how the positions are changing with time, right. And I also know the momenta, because momenta is simply mass multiplied with the acceleration, that is mass multiplied with qi, right. So, let us say if I start with a given value of p and q, that means I start with given coordinates and momenta of the system. I know how they will evolve with time if I know the forces acting between the particles, or forces acting on that particular particle at this moment, right. We'll just now we can discuss like what is the force acting on the particle I, right. So, Fi is the force acting on particle I, right. So, in terms of our space representation, I only need to know my initial state gamma naught, that will be corresponding to some initial value of p naught and q naught, and that will be the initial condition for this second order differential equation, because this q dot is something like d2q by dt square, right. So, solving a second order kind of a differential equation, and we know the initial condition in terms of the momentum and the coordinates of all the particles. So, we can do it for every particle in the system, and then we know how the system is evolving. Now, this kind of makes it clear why I used a delta t, why I used a discrete domain, because we are solving a differential equation. So, in a sense, to find q or to find the momenta, we need to do some kind of a differentiation and integration. The numerical way of doing that is by discretizing the domain, and that is what we have already done in the time space. Now, why do I say that we cannot solve it analytically? The reason being that how will I find these forces acting on the particle? That is first point. And the second point is how many equations do I have to solve? So, let us say even if I know the forces by whatever means, then this quantity essentially is meaning how many differential equations. So, you have this equation written for each of the n particles in the system. So, you have n second order differential equation for the acceleration and n first order differential equation for the momenta, right. And clearly there are too many differential equations because we are dealing with n that is really large, that is a thermodynamic system, right. For 2 or 3 particles we can clearly do that. This is how you do a multi-particle system in classical mechanics, but as soon as the number of particles become large, this becomes a very much intractable problem for analytical stuff, and therefore, there is no way we can do that. It is more important point because these forces are also kind of complicated. So, in a classical system, the way we are used to seeing, the forces are often external to the system. Let us say when the apple is falling from the tree, then it is experiencing a gravity force, and that is given by the mass of the apple multiplied by the gravity. The force is external to the system, right. What we are dealing with are systems at equilibrium. So, that implicitly means that there is no external force acting on the system. In most cases where we will apply molecular dynamics in this case are when we are interested in the equilibrium behavior, that is in the absence of any external force. The external force can also be accounted for, and there are a whole set of methods to do that. We will briefly touch on that later. But for the time being, let us assume that we are interested in equilibrium. So, the forces are not external, right. So, then the only way the forces appear in the system that I have drawn is because of forces between the particles of the system, right. So, every 2 particle will experience a force. So, let us try to look at that in a bit more detail. So, let us say these are the particles that I am looking at, right. Of course, there are too many of them, but just for the sake of drawing, I am drawing only few particles. So, let us say if I am interested in this particle number 1, and there are others labeled 1, 2, 3, 4, 5, 6. Keep in mind these labels do not have meaning because the particles are indistinguishable, but that is besides the point. For every particle, it is experiencing forces from every other particle in the system. So, if I have to find the net force on the particle number 1, it is going to be a sum of the forces because of every other particle in the system, right. So, let us say if I want to look at f of 1, that is going to be the force between 1 and 2, the force between 1 and 3, and the force between 1 and 4, 1 and 5, and 1 and 6. In general, what we can therefore say is the force acting on any particle I in the system is sum over all the particles in the system, let us label them J, except that particle itself. So, one does not apply force on itself, right. So, if I sum over all the other particles apart from the particle I and find the forces between them, we have essentially find the total force acting on this particular particle. So, Fij is the force acting on particle I because of particle J. It turns out that instead of forces, it is many times more convenient to discuss in terms of the energy of these interactions, and ultimately forces and energies are kind of related, right. The only difference is that the force is kind of acting on every particle, right. So, it is a well defined thing to look at the force on every particle. Energy on the other hand is defined globally for the entire system, right. So, there is not much meaning to look at the energy of one of the particle in the system. Of course, that can be defined, but in general the energy is typically defined for the entire system that we have, right. But nonetheless, the force and the energy is defined in this particular way. So, I can write my F as the gradient of the energy between the particles, right. So, at any point in the space, if I find the gradient of the energy, I will get the system. So, U is defined globally for the system. Of course, that does not mean that U does not depend on the particle position, U depends on that. For a given configuration, you will have a given value of U. If I take the gradient of that, that will give me the force acting at any point in the system, right. So, now it is defined in a continuous domain, so as to speak. Because we are dealing with large number of particles, it is not really greatly important, right. So, del can be defined as the sum over dou by dou qk, where k are the components of the coordinate. So, 3-dimensional space k will go from 1 to 3, multiplied with the unit vector in the k direction, right. That is my gradient operator, right. So, instead of saying the forces acting on all the particle, I can then say that I can find the U of the system. And what does the U of system come from? The U of system come from the interactions between every pair of particle. That means, I will sum over all particles, and for that I will again sum over all the particles except the particle I, and I compute the energy of interaction. Let me use small u to represent the energy of interaction between particles I and J, right. So, this is the interaction energy between particles I and J. And clearly, when we do that, we will be counting every interaction twice, because let us say if I count the interaction between 1 and 2 in this picture, in the sum you will have U1 2, but then you will also have U2 1, but both are representing the same energy. In terms of forces, they are acting on different particles, but in terms of energy, it has to be counted only once, not twice, because every interaction is only contributing once to the sum. So, therefore, we need to divide this by 1 by 2. So, now what will this uij or fij depend on, right? So, clearly you may imagine that as the particles come closer or farther, right. So, keep in mind that I have been trying to develop a generic representation from day one. I did not say what are the interactions, right. So, let us say if the particles are coming farther or closer, what is going to happen? The forces has to change. It does not matter what forces are there. If it is Coulombic force, it is going to change. The Coulombic force goes like inverse of the distance between them. If it is van der Waals force, then also it is going to change, right. It is very intuitive to see that the particles farther apart will have lesser forces and therefore lesser energy of interaction, and particles closer will contribute to more energy or will have more forces, right. So, therefore, this is going to depend on the Ri minus Rj, that is the separation between the two particles I and j. I can call this something like Rij. So, therefore, this will also depend on Rij, right. So, we will see later that we also may have to worry about the orientation of the particles if we are not doing spherical particles. So, something else may also come as an argument here. Let us say the angle between the two particles if they are not spherical, but nonetheless that will also be changing as the states are changing, right. So, it is a function of the separation and it is a function of the relative orientation, right. So, we can say Rij comma relative orientation of the particles. We can leave it for later because I am assuming that the balls are spherical in the picture. So, in that case the orientation is not so important. So, going further, what we can also say is that in most cases that one can imagine, there is no directionality to the interactions, right. So, let us say for example, you have 1 and 2 and they are, let us say here or here, let us say 2 was here. As long as the distance is the same, we may imagine the forces are also going to be the same, right. So, it is not that the vector distance is important. In fact, it is the magnitude of that is more important. That is not completely true, particularly when there is some directionality to that. We can also worry about that later. So, assuming spherical particles and assuming no directionality, that is true for almost all the cases that we will discuss in this particular course, we can say that we will not worry about the vector distance, we will worry about the scalar distance. We can say we want to compute uij as a function of Rij. And finally, if all the particles are identical in the system, then we can now say that all the particles will have the interaction energy with other particles changing by the same function, right. So, let us say for example, all the particles have the same mass, same charge, everything, they are the identical particles. In that case, you will not have different mathematical forms of interactions between them, right. So, in general we can write U of R for one component system. If you have a multi-component system, in that case you will define something like U alpha beta R, but then the alpha beta refer to my species, right. Let us say you have species A and B, then you will have UAA, UBB and UAB, right. So, you will have different mathematical forms for different pairs of species, not at the particle level, but at the level of species. For a one component system, you will have a single u of r. So, now the idea is how can I represent this u of r. So, then to conclude the discussion, our objective is to find this mathematical form u of r between every pair of particles or the pairs of species, whatever. Once we have that, then we can find the Hamiltonian. Why I am saying that? Because once I have this small u, I can find the capital U, and the kinetic energy is a function of the momenta, and momenta anyway I can find in terms of the generalized coordinates, right. So, the only thing that we have to find is the energy of the system, and the energy of the system will be characterized with this u of r. Clearly, if I look at different states with different p and q values, in that case the r will also change between every pair of particle, and therefore, the energy will also change, and therefore, the Hamiltonian will also change, right. But this is I would say the basic mechanism that we can think of, right. And that is what is done in a molecular dynamics simulation. You give a feed or input value of u of r, and I will discuss in the next class that what exactly it is called and so on. That becomes the feed variable. You find the Hamiltonian or energy, and you solve the Newton's laws of motion, and the particles evolve, and you essentially have the description of the trajectory in terms of gamma of t. And once we have that, then we can find the average value of the property I am interested in as time average of m of t, right. So, the next lecture we will discuss how can we estimate u of r, or what are the ways we can represent this u of r. So, with that I wish to conclude here. Thank you.